this time we want to generate all string combinations, and of course combinations are a very broad subject, and we can have combinations of strings, as we will do here, where we will deal with subsequences, and there is subsequence, substring, subset. Those are all connected but different and have different consequences. And so this time we have subsequences, and subsequences are connected with combinations. So we'll try to demystify combinations a little bit. I think it's also really important topic, not only for coding interviews, but in general, since it deals with both computer science and math. And maybe first let's start with the combinations in general, or what is the difference between combinations versus permutations. Since when we talk about combinations, we also usually talk about permutations. So what's the difference between the two? And we said already that combinations can deal with strings, but also in general with any sort of collection. And by collection, I don't mean just collections in computer science, but any kind of collection. And both combinations and permutations want to have the number of, or how many ways we can get from one bigger collection to like subgroups or subcollections or arrangements, as they are called. And so how many arrangements can we get from this one collection? And if the order of arrangements matter, then we deal with permutations. And if the order of arrangement doesn't matter, then we deal with combinations. So they sort of ask the similar question, but combinations are a little bit easier because we disregard the order, and that means that we will have much less, especially for bigger numbers, combinations than permutations. And for combinations, you can think like you can build a mental model with I have this story that I like to tell. Let's imagine that we are a king, or there is a king which has some enemies to fight, and he has 3 warriors, A, B, and C. And he can decide in what kind of way he can send the warriors to fight that enemy. Either he can send all of them together, like in one batch. He can say, A, B, and C, go now and fight. Or he can say, A, go now, and then when A doesn't come back, he sends B, then he sends C. Or there are also other possibilities when he sends A and B together, and B and C together, and so on. So in total you would have 7 possible ways. And once he selects the warriors, it doesn't matter if he says like B and A go or A and B go. And it's if for that particular scenario, the order is not important. That's why we would say that here we are dealing with combinations. But there are scenarios, of course, when the order does matter. Let's say we have numbers or digits, and we want to construct a pin or a code. In that, for that sort of thing, the order matters, of course, because let's say 2 to 1 would be different than 1 to 2 or 2, 1, 2. And those would be all different codes. So sometimes we have sometimes the permutations are a better answer, and sometimes combinations. And I hope that that explanation was sufficient. And now let's read the description. So given a string, generate all possible combinations, this time subsequences of its characters, and combinations must include all subsets of characters from length 1 to n. So we disregard the empty like subsets, and at least we would take a single character. And then we of course have, like in the story with king and warriors, all kinds of other possibilities, so either single character or 2 characters or 3 characters and so on, up until the full length of the string. So from 1 to n, and order of combination does not matter. This is of course understandable, since that's the definition of combinations. And there are some constraints. The input string will consist of unique lowercase letters, and the length of string will not exceed 20 characters. And that's also important because to generate combinations, even in an efficient manner, it's still takes a lot of time and a lot of CPU power, and very easy you can overload your CPU if you will try to input much longer strings. So even, let's say, if you try it for 25 characters, maybe for 30 characters, you would see that it will take very long time for the computer to compute all the possible combinations. Yeah. And definitely 100 or 1000, that would be definitely something that takes a long time. And here is an example. Let's say we have this ABC, yeah, and the following combinations are possible: A, B, C, AB, AC, BC, and ABC. Yeah, and if you count how many of them there are, then we have 1, 2, 3, 4, 5, 6, 7. Yeah, and the characters, number of characters is 3, and 2 to the power of 3 is 8. Yeah, so the number of combination is always 2 to the n minus 1. Yeah, so in this particular case, it's 8 minus 1, so this is 7 combination. And here we have a smaller example with 2 characters. 2 to the power of 2 is 4. 4 minus 1, 3 possible combinations. And so here we'll implement 2 solutions, one recursive, which I think is more, I would say, natural when it comes to combinations, and then iterative using bitmask. And I think this is also something that is definitely understandable, maybe not as easy to understand, but also you should know about bitmask and bitwise operations, and definitely something to learn. And then we just have some test cases to verify whether what we created has any standing, and that's it. So let's start with the first implementation, recursive. So here we will divide it to 2 parts. There will be the main function or the public interface, where which will be called from the tests, where we accept this single string, and it will return whatever this helper returns, and the helper itself will implement the recursion. So here we will just call the helper, and simple solution helper, which accepts string, index, and current character. And for now, let's leave it the way it is, except maybe for string. We already know that the string is the string that comes from the outside, and index, of course, we start from 0, and maybe we can just fill it, since I think there's not much philosophy here, even without this part yet ready. I think it's sort of understandable that we will pass first of all the string, which comes from the outside. We will start from the 0 index, and then the first character will be an empty string, so we'll start sort of outside of the string itself. And here comes the whole magic. We will store our results in std set of strings. We'll call it result, and by the end we'll return the result. And every recursive function is divided into this base case where some condition is met, and when this condition is met, we exit the recursion, and then the other case or the recursive case where we do some stuff. And so there's this base case and recursive case, like this, I think. And in the recursive case, we will call, of course, the function that we are now defining. The function calls itself. That's the idea behind the recursion, and we will call it 2 times, since each time whenever we want to create our combinations, we have, that's now the main part, we have 2 options. Either we can take the character or leave it. Always just 2 options. That's why we will have this 2 to the n minus 1 combinations in the end, yeah, since each time we can either take the character or leave it. Yeah, so on this example with ABC, first we take A, and the very first combination is just as A, propagated till the end. Then we have B, either we take this B or we leave it, and if we leave it, we reach the C, and the C can be propagated till the end, and then A1 version when it was just taken once and then left with all the other times will just yield this A alone, but the other case is when we add B as well. So for example, A and B and so on. So each time we have those two choices, either we can take them or not, and in the base case, we will terminate, of course, you can guess already, probably from this argument, when we reach the end of the string. So if index is equal to string size, that means that we have reached the end, and we have to check if the current is the one, like this subsequence that we are propagating. If it's not empty, then we can add it to our set. So result insert current, and we can also add proper curly braces and return the result. That's the whole backspace. So what's happening here? We just propagate whatever was here till the very end of the string, and then we insert it to our set. And here, once we, in the recursive case, we decide about those two cases. So with, one will be with the current character, and the other will be without. Let's do first with. Simple solution happen. And we put the string, we don't change anything. The index gets incremented by 1. And we pass the current plus string on index I. And that's when we include the current character. And the second is without, which is almost the same. You of course have to still pass the string. It's the same string for both cases. Both cases we increment the index, but we just pass the current. And the very first current, as you can see here, was this empty string, which would reach the end, but wouldn't be inserted to the result. The second current that would be created by adding to empty string the first character will be A, and it will also be propagated and inserted at this place, and then B, C, A, B, and so on. And now we can expand our result. We can merge what we got from both cases. And let's compile combination. Did I make some? Okay. I was not declared. Here I see it. It's called index, not I. In one place I changed it. Index. Okay. And here I forgot STT. Third. And that's it. So 2 typos. Now let's compile, and the first solution passes all the test cases that I've prepared. You can also try to expand the test cases if you want, and let me know if it covers all the possibilities or there is something that I missed. Now let's deal with the second example, bitmask and plus iterative. So this one was recursive, and here we are using bitmasks plus iteration or loops. So the idea here, as we said already, is to use masks. And let's say we have our example APC, and we apply the following mask 0, 0, 1. And so the 1 represented in binary, and I use just 3 digits because we have 3 characters. And that mask would, after applying that mask, we would get single character, the one at that position, which is 8. Then the second mask that we would apply is 0, 1, 0, and that would be. Then the next one would be 0, 1, 1, and that's binary 2, that's binary 3, and we would get A and B, and so on and so forth, up until we reach all combinations. So we need still our std set of std strings. This time I try to not forget, and we can call it result still. Then we return the result, and then we need n, not auto. Let's just use int to be on the safe side, and we can cast it using static cast int size of the input string. That's it. We have n, and we will have masks starting from what? From 1. Oh, int first mask is 1. And how many we have? We said already when discussing the recursive case, each time we do or we choose between 2 options, either we take the character or we leave it. So in total we have 2 to the n masks, minus 1, but we start here with 1. So mask less than 1 shifted by n. Plus mask. Those are all the masks. Now for each mask we have one combination, which is a string. And this combination we insert to the result. At the end of the loop, result insert combination. And now how can we get this combination? We have to again loop, but this time not till 2 to the power of n. Those are the masks. Now we loop through the characters in the string. Yeah, so for int I equals to 0, I less than n, plus I, we do what? We check whether we have this match. And how do we check for this? Check whether mask and 1 shifted by what? By I match. If so, we add character on that index. And that's it. Now we generated a combination, we insert it to the result, and by the end we should have everything the same way we had with recursive case. So now let's compile combinations exam, and all tests passed successfully.